maybe we'll give it one more minute. There's still the odd person coming in. Okay, maybe it's a good time to make a start. So if you look at, sorry, I just posted to the chat the Jamboard, which is where Evita is writing, so you can go backwards and forwards through that. That's the thing that's on the screen share as well. But if you want to go backwards and forwards, then you can do that directly at the link. So great. Well, it's a very big pleasure to have Evita again today. So this is the second lecture of her 3-lecture course. The last one is on Thursday at the same time. So over to you, Evita.
Thank you so much. Thanks everyone for coming or coming back. So as I said yesterday was the most probabilistic lecture. Today we're moving to the spectral properties of the transition matrix and how to use them to provide answers for mixing. So today and tomorrow, well, mainly today, we're going to be looking at upper bounds for the total variation distance. Yesterday, we played with lower bounds for total variation distance and separation distance. And indeed, this L2 bound is the technique that we're going to use. So at first I'll focus at the technique, introduce it. I have to apologize to the experts for saying things that they've probably seen multiple times. Basically, the idea is to do Cauchy-Schwarz and bound the L1 norm by the L2 norm, and then use the spectral information of the transition matrix to study the L2 norm. So let's write that. We're going to use the spectral information of the transition matrix today. And our hope is to get sharp answers. So let's say this was the total variation distance. So this will lead us to the discussion of cutoff. I'm not going to say as much as one could. I'll just define it and show you an example. I do want to say that the technique has some restrictions when we want sharp answers. It is mainly applied to reversible Markov chains, and I will redefine reversibility. But we're usually okay with this restriction. Many of the applications we care for are reversible. And I will finish the discussion by applying the L2 bound, and actually this will be half of the talk today, to the non-backtracking random walk on Ramanujan graphs. And soon we'll see that this is not the traditional way to define the non-backtracking random walk. It's a different one that turns out to be reversible. So the L2 bound can be applied. So this last application is can be found on a joint paper with Peter Sarnak. Okay. So this is the outline for today. And I do want to remind very quickly the definitions that we saw last time. So we always have a finite configuration space. In this lecture, n will be the size of x. Then we consider a Markov chain on this configuration space with transition probabilities p, x, y. This means, if at time 0 we are at x, we land at y after one step with probability pxy. We collect this information in one matrix, which we call the transition matrix. And the main property, basically definition of this matrix, is that the tth power, the xy entry of the tth power gives us the probability of moving from x to y after t steps. And under certain conditions, so if we're aperiodic and irreducible, I'll explain again in a different way what that means. There is a unique stationary measure that we converge to. So this means that if we take really high powers of this matrix, the rows are going to start looking like this probability measure P. Finally, the last thing that I'm going to need from yesterday's lecture is the total variation distance, which is defined as 1/2 the L1 norm. The L1 distance, I mean, between these two probability measures. When we fix the starting point x, we can call this dxt, but usually we like to take the worst case starting point by maximizing the total variation distance over all starting configurations. And then the mixing time, which is the main question, is, if you give me an epsilon, I should tell you what is the first time that this total variation distance becomes less than epsilon. So basically, we want to know when we are really, really close to this stationary measure, and epsilon determines how close. So I know this is a quick overview, but we said these things last time. Let me quickly remind you what reversibility is and a few properties that will also come into play when we discuss eigenvalues. So, we say that the Markov chain, well, the transition matrix P and its probability measure P is reversible if this equation is satisfied. Yesterday, I explained to you that basically, if we sample the starting point with respect to pi and then take a step, this should be the same as if we had sampled y instead of x and then taken a step. Today, we're going to look at it more spectrally, meaning that the property that this equation gives us is that this matrix AXY, which is the square root of pi of x over pi of y times the transition matrix, this is symmetric. This is a corollary of this equation. Just play with it. Symmetric. This means that this AXY has real eigenvalues, and we also can talk about an orthonormal eigenbases. This is the information we're going to be using very, very soon. Okay. Also, before going there, I want to define the Markov chain graph because I'll be going back and forth all the time. So this is the first definition. So G is the Markov chain graph. I'll be denoting it by G, I mean. The vertices are X. X is the vertex set. And two nodes will be linked. So they form an edge. If and only if the probability from going pxy, basically, probability from going to x from x to y is positive. Okay. And we will be in the reversible case, so I don't want to talk about directed graphs. This will be an indirected graph. In this case, by the way, just because it's easy for us to define this now, giving connected corresponds to the Markov chain being irreducible. And this graph being non-bipartite in any way corresponds to xt being a period. So this is an easier way to explain these notions. So connectivity means I can get everywhere I want to, and being non-bipartite means that there are no nodes that I visit only on even times with some parity anyway, and so on. We want to be able to get lost in the graph after a specific amount of time. So this is basically, these were the definitions I wanted to tell you. Actually, there is one more, which is that we tend to diagonalize the transition matrix with respect to a specific inner product. That is just convenient. Even if we don't consider this specific inner product, the equations I'm going to be writing will change in a specific way. However, if you look at textbooks, usually they consider this inner product. So if we take two functions, or x and g, I will be calling, so the vectors will correspond to functions now. So a vector, the coordinates will be indexed by x. X is a finite space. So you might hear me call eigenvectors eigenfunctions instead, because really functions and vectors here are the same thing. Anyway, so the inner product we consider between these two functions is with respect to the stationary measure. So here x is a finite space, so this sum makes sense. And I have defined L1 norm for you, a total variation distance. Let me also say that the L2 norm that will be handy is this one. So we will see this term appearing again. So we do take again the ratio between the transition matrix and the stationary measure. How far away is it from 1? And the L2 norm again will be with respect to this inner product. Oh, well. And we'll see that this is exactly what works well when we do the Cauchy-Schwarz, meaning that play a little bit to see that 4 times the total variation distance squared. So this is basically the L1 norm. Play with it and do Cauchy-Schwarz to get that this is less than this L2 norm that I wrote. It's a nice exercise. Get your hands on this type of computations. Okay, now I can start talking about the eigenvalues, how they connect to mixing, the Markov chain in general. What can they tell us? So let's write here the spectrum of the transition matrix. Let's move this up. And I'm going to break a very important lemma into 2. Everything I'm going to write now can be found, say, in Levin, Perez, Wilmer. That's the standard book on Markov chains. And many other Markov chain textbooks. So again, we have a reversible. Let this pair be a reversible Markov chain. Now, as I said, we can use the spectral theorem to decompose this. Let L1, lambda 1, lambda 2, and so on, lambda n. Be the eigenvalues, so we order them. We know they're all real because I explained already that this key is basically symmetric by doing this transformation. And we also denote by, actually, let me be consistent with my notes. Let me start from 0 here. And the corresponding eigenfunctions will be f0 through fn minus 1. So by eigenfunctions, of course, I mean that all these fi's are from x to, well, r, but anyway. And then if we take the mean with respect to the transition matrix, this will be lambda times f. And they are also orthonormal with respect to the stationary measure, that the inner product that we defined. Okay, so let's say a few things about these things. So the first thing that we can say is that all these eigenvalues are between 1 and minus 1. In fact, the first one is always equal to 1. That is a very standard fact from graph theory. You know, when you have regular graphs, basically all the eigenvalues are in this regime. The second thing that I want to say is that lambda 1 is less than 1 if the Markov chain graph is connected. So suddenly these algebraic features start telling us something about geometry. And the third thing I want to write right now is that the last eigenvalue is actually strictly bigger than minus 1 if the graph is not bipartite. I keep misspelling bipartite. Okay, so to prove these types of things, especially B and C, one has to use the max principle that, you know, if you take an average and the max is attained in the center, then around you, you have to be equal to, you have to be constant, basically. Again, I refer you to Levin, Perez, Wilmer for this. And now I want to show you how to use this type of things, this information, to bound total variation distance. So the actual L2 bound by the way, this type of things were the first lecture of Percy Diaconis's graduate class on mixing times. You know, he always starts with this, explaining how to use eigenfunctions and eigenvalues to bound the total variation distance. So again, the setup is the same. So we are reversible. The lambda i's are the E values, and the Fi's are the orthonormal eigenvectors. Then the main thing that I want to write is that indeed 4 times the total variation distance squared this is less or equal, as we saw, then the L2 norm, and the L2 norm now is bounded by this quantity. I'll explain it in a second. Okay, so here these are all the eigenfunctions, but the first one evaluated at the starting point. And here are all the eigenvalues but the first one. So if we take a moment to notice what this right-hand side says, if we are in the case where all the eigenvalues are strictly between -1 and 1, that is when the Markov chain is aperiodic and irreducible, these numbers are strictly less than 1. So taking t to infinity, this sum will converge to 0. Okay, so this already tells us that this is a way to prove that irreducibility and aperiodicity imply the convergence. But now we can also use the specific information to say how fast this convergence happens. The key facts that I want to write here, because they're either useful today or they will be useful tomorrow. The key facts that this proof uses, and again, you can search for the proof at Levin Ferris Wilmer, is that when we diagonalize and use reversibility, we have this very nice expression that the xy entry of p to the t is given in terms of the stationary measure and the eigenfunctions and the eigenvalues. So once you plug it in the L2 distance, this ratio will cancel out, and then you can do Cauchy-Schwarz, basically. This -1 will cancel out with this -1, and then you do Cauchy-Schwarz to get this. And you use we have an orthonormal basis. The second fact that we might need, at least today, is that if we fix the starting point x and we add the square of all eigenfunctions at x, this is 1 over the stationary measure. These are really nice exercises to play with. For now, I'm just giving them to you. I'm not going to prove them so that I can move on to the application that I want to show you. But at least the first fact is going to be important tomorrow. So I'm going to use it again. And now I want to go towards Ramanujan graphs. So hopefully it won't be as trivial anymore to people who are familiar with the topic. So an application on Ramanujan graphs. So actually, before I go there, maybe I should say one more thing so that this application makes more sense. If we look at this L2 bound, there are two ways to go. Either, you care about your favorite Markov chain. So you have a specific example you want to study for your own purposes. And then you need to find, you need to diagonalize P to use the spectral information. And the main way to do this, I mean, sometimes we're lucky, sometimes the Markov chain is, the space is very small and we can do it by hand, like a simple random walk on a cycle, for example, or on a path. But usually the configuration space is bigger. And the main technique that I'm aware of is using representation theory. And this technique usually works when the graph is a Cayley graph and the generating set is conjugacy class. This is the standard technique due to Diaconis and Hani. So when we cannot find explicitly the eigenfunctions, then maybe we care about families of graphs that have some special property in terms of the spectrum, so with special spectrum. And today, we're going to be talking about the second thing. I want to avoid having to teach representation theory in a 3-lecture course. So I am going to instead talk about Ramanujan graphs. And again, everything from now on is joint work with Peter Sarnak, as I said at the beginning. Let me define the non-backtracking random walk first of all. Okay, so we will have a graph G. The vertex set will be X and the edge set will be E. And the non-backtracking random walk will be happening on X, so on the vertex set, is defined as following. KTXY is the number of non-backtracking paths between X and Y of length T. So X0, X1, maybe X1. XT, the starting point is X, the finishing point is Y. We are walking on edges, so this path is our path, and we have that xi plus 1 should not be equal to xi minus 1. So we should not be going back. This is not the traditional way to define non-backtracking random walks. Usually, non-backtracking random walks are defined on the edges. The good property here is that this thing is symmetric. Of course, to turn it into a transition matrix, we should normalize. So we should divide by the number of such paths. So we are in the case of a deregular graph in this talk. And this is going to be the definition of the matrix. This is the matrix we're going to be studying. And the point is that as t goes to infinity again, this will be converging to 1 over n. Again, n was the size of the vertex set. Okay, and we want to study this random walk. We want to study the mixing time using the L2 bound. Okay, and we're going to do that for Ramanujan graphs. So let me give you the definition of Ramanujan graphs. Ramanujan graphs. So they are indeed deregular graphs with the property that when we look at the adjacency matrix, so I'm going to write the eigenvalues a little bit differently. The biggest eigenvalue now is going to be D, not 1. We can divide everything by 1 in a second. So these are the eigenvalues. Beta 1 is less than 2 square root of D minus 1. And similarly, the last one is bigger than minus twice square root of D minus 1. This is the definition. So if we divide everything, then we get the corresponding eigenvalues. In graph theory, usually we don't divide by the degree. So that's why I wrote it this way. But really, if we divided everything by D, we would be getting the same expression that I was writing earlier. So we impose a very big restriction on the eigenvalues, and we call these Ramanujan graphs. why do we care about these things? Are they made up? Where does this this quantity 2 square root d minus 1 come from? Well, basically this bound. So let me write it again. So the restriction was that we had everything here, maybe with equality. Sorry, should have put equality earlier, for every I other than 0. This comes. This is the optimal bound that one can hope. You cannot have a smaller bound for the eigenvalues, and this is a result to Alain Bopana. So this is one natural way that that this could come from. And these are, let's say, these Ramanujan graphs turn out to be maybe the best family of expanders that one can hope for. They have all sorts of beautiful properties. First of all, was a while ago, since Lubotsky, Phillips, and Sarnak proved that they exist. And ever since, there have been more proofs, where more properties of these graphs have been explored. But in particular, in terms of mixing, because this is the subject today, and I don't pretend to be an expert on Ramanujan graphs in general, but mixing is something that interests me. These are the type of graphs where we expect the fastest mixing, basically. And in terms of simple random walk, which is the usual walk that we consider, this has been thoroughly studied by Lubotsky and Perez. Soon I will give you the exact things that they found. And they used a different version of the non-backtracking random walk to prove cutoff, to prove sharp answers. Anyway, so let me give you the main result and then compare with what Lubotsky and Perez did. So dt was the total variation distance. Let's not forget that, because in the theorem we are going to use this. So if G is a Ramanujan graph, let's say D, it's a deregular graph, and let's call P to be d minus 1, because as you saw, it appears all the time and it's a bit awkward to write it again and again. The first thing that we proved says that if one takes this many steps, and maybe I'm slightly cheating because maybe there is another constant on the window, but I don't want to make it too intimidating, then the total variation distance is less than epsilon. So we say that this is how many steps we need to take, log Pn, and then we have a smaller order term, which is log n. Then the total variation distance is less than epsilon. But the second part is that if we further assume that the girth of G is bigger than a constant times log n, so delta is a constant, then we can get a better window than if t is log Pn plus log P 1 over epsilon, then the total variation distance is less than epsilon. And this is basically what this discussion is all about. This is why we consider this new non-backtracking random walk. We could get a better window than the usual non-backtracking random walk. Let me finish the picture here before comparing it with other theorems and explaining what cutoff is. There's a very standard thing, which is the lower bound is basically trivial to prove. So combined with the fact that if we take a few less steps, so if t is log Pn minus this many steps, then the total variation distance is big. And this is a very easy argument. Basically, you cannot reach many vertices if you take only this many steps. So this is very standard. And we notice that the main term here, both on the upper and lower bounds, is the same. And then we have a smaller order window that tells us, how much we need to walk for. And this theorem describes what we call the cutoff phenomenon. So I want to tell you a little bit about the cutoff phenomenon before proceeding to how one proves this theorem. Okay. So what this theorem tells us basically is the following. And if you are interested in mixing times, this is a picture that you have to get used to seeing. So if we draw a diagram where the x-axis is time and the y-axis is the total variation distance, what is happening is that the total variation distance starts from 1. So we are really not mixed when we start. We know the starting point. But then very suddenly, at log Pn, there is a sharp transition where from unmixed we go to a very well mixed situation. And the window Wn is basically what I want to discuss here. So the window is the radius of this interval, not the diameter. So let's say Tn here. So the cutoff phenomenon usually is described by two equations. The first one is that if you take, well, actually no, the first one is that we have two quantities that depend on the size of the configuration space, Wn and Tn, with the property that Wn is little o of Tn, so smaller order. And then if we take Tn steps, let me write it differently. If we take Tn steps plus a little bit more, Wn determines how much more, and then we take a limit with respect to n, and then a limit with respect to c, then the total variation distance will be going to 0. This describes this part of the picture, that we are going to 0. But if we take less steps, then we will be going to 1. So we are not mixed at all. And this is what we call the cutoff phenomenon. This is one of the most central questions in Markov chain mixing. When does this phenomenon occur? Do we have an if and only if criterion, and so on? So, and even though we have a necessary condition, we still don't have an if and only if criterion that works in a big generality. We have an if and only if criterion for special cases like random walks and trees, for example, and so on. And so the community does care a lot about examples where cutoff occurs and the techniques for proving cutoff. So back to Ramanujan graphs. So what Lubetsky and Perez proved, they proved, first of all, for the simple random walk, that cutoff occurs, and it occurs at log Pn, just like the non-backtracking. Oh, sorry, that's non-backtracking. here I should have the speed. Oh, I think I don't want to miswrite their theorem. They do prove that cutoff occurs there, and they get the correct window as well. The window comes, the cutoff window and the cutoff time are sharp because of a central limit theorem. To get the cutoff, they do it via the non-backtracking random walk on the edges. And their answer isn't as sharp as it could be, meaning that, and that's why I'll focus more on the non-backtracking random walk. They do get that the cutoff occurs at log Pn, but the window is of order log n. And so this is why I'm saying that part B is what we were hoping for, because we show constant window. So that's a significant improvement. Also, the technique that I'm going to show you has certain advantages to the technique that Lubetsky and Perez considered. And in general, the non-backtracking random walk on the edges has been extremely useful in studying cutoff for simple random walks on other settings, for example, the Erdős-Renyi random graphs. So definitely their technique had a very, it is a very important technique. Back to our problem, however, what is special about our non-backtracking random walk? Why is it making things easier? The main property, so KT, remember, was the number of non-backtracking paths. From X to Y. So let me put here the XY entry just to have it in front of us. The main property that we use, and it is a main property that Lubotsky, Phillips, and Sarnak used when they proved the existence of this graph, is that it has a very nice polynomial expression. So if A is the adjacency matrix, of the Ramanujan graph, then KT can be expressed as follows. Let me copy this correctly so that I don't write it wrong. Okay, I'll explain what each term is in a second. So on any graph, not only on Ramanujan graphs, this equality holds, where these are the Chebyshev polynomials of the second kind. And these are the Chebyshev polynomials of the first kind. We have formulas for those. I'm going to write it in a second just for completion. Okay, this is the adjacency matrix, as I said. This is exactly the term that we have from, this is the bound from the Ramanujan graph. Okay, this is the restriction that we imposed. And these are just some extra terms. So basically, what this tells us in terms of the spectral information is that if we set Qt to be the polynomial given in this equation, so this is just a polynomial in the real variables. It will be real variables in this setup at least. If beta I are the e-values of the adjacency matrix, then qt beta I are the e-values of kt. So we can diagonalize immediately kt using the eigenvalues of A. And they also share the same eigenbases. The orthonormal eigenbases. Also notice that the eigenvalues that we're going to plug in here are all going to be in absolute value less or equal to the denominator. So we really are plugging in quantities that are less or equal to 1. And that's good in terms of Chebyshev polynomials. Let me write down what Chebyshev polynomials are, the formulas, just to see. So let's start with the first ones. So tt of cosine theta is equal to cosine t theta. That's the second term over here. And then ut of cosine theta is equal to sine t plus 1 theta over sine theta. Given the time, I'm writing these formulas and we can forget them. I don't think I'll write them again. But I just want to say that this is why it is important that, you know, if the values that we plug in here are indeed between -1 and 1, we can find a nice theta that achieves that value, and we get real outcomes, no complex numbers involved. And so the point is to you know, do trigonometric manipulations, use the formulas for these quantities. So I duplicated the page just because I don't want to have to write again this expression, or at least I can keep qt. Ah, yes, good. Yes, I should have come here instead and erase things here. Sorry, technical problem. But anyway, I want to just keep this guy, this polynomial, just to keep it in mind, and study it for 5 minutes. I mean, I don't think it makes sense to really do all the computations. Okay, here we are. The main thing that we use is that this polynomial, when we plug in the eigenvalues of the transition matrix, let's see, yes, it gives this bound. And this really comes from simple trigonometric manipulations. Actually, this +1 might be a +2, meaning that when we have this bound, when we want to bound the Chebyshev polynomials for the second kind, remember we just had this thing. Everything is real here. This is just less or equal than t plus 1. And when we do the same thing for the Chebyshev polynomial of the first kind, this is just the cosine t theta. This is less than 1. This is the simplest bound that we can consider for these terms. So, and just using this extremely naive bound, we already retrieve part A of our theorem, which says that 4 times the total variation distance squared is less or equal. I'm just going to write what plugging everything in the L1 in the L2 norm gives. Yeah, the t plus 2 comes from these 2 terms. Okay, and this just really means that we need to take this log-log window. So if we take t to be log pn plus c log n, this becomes small. Okay, so it is as simple as that to retrieve part A. For part B, we had to do something slightly smarter, which uses essentially the girth. So the girth assumption that we had is that the girth should be of order log n. And basically, let me say here, if the girth is of order log n, the graph looks like a tree around the starting point for a big time. And the non-backtracking random walk on a tree is very, very easy to play with. There are not that many paths between X and Y on a tree. This can essentially be used to prove two things. The bad terms on the L2 norm really do come from the Chebyshev polynomials of the second kind. So we do have at first to prove something like this, that they're not that bad when, so this is the Chebyshev polynomial of the second type. They're not that bad if L is smaller than the girth divided by 5. That's the first lemma that we prove, which uses essentially that when we take this many steps, we are walking on a tree. And the second thing, which is more playing with trigonometric stuff, is that if we write the time as something like girth over 5, we divide it by girth over 5, basically, times x, then we can really bound this term by this x, basically. So it doesn't make sense for me to say more than just these two facts. These are the main two tools. We plug them in the L2 distance and they give us exactly what we want. This is just trigonometric manipulations. This is more conceptual because it uses the fact that the non-backtracking random walk on a tree is very simple. Finally, I want to just say one more thing, which is that, okay, the argument, at least for part A, which is basically the same as the result of Lubetsky-Perez, was trivial to prove. It was extremely easy once you know this polynomial expression. The other advantage to this technique is that it can be generalized to other expanders. So what if we don't satisfy the Ramanujan property, but we are an expander and our eigenvalues are spaced well? So a graph G satisfies, so let G be an expander first of all. G satisfies the density property. If the eigenvalues that exceed the Ramanujan bound are spaced nicely. So if we write the eigenvalues as 2 square root pi cosine theta j, okay? When theta j is real, then we are on the Ramanujan bound. When they're complex, we're going to write them as this. And we want the number of the phi j's that are bigger than an alpha. So for every alpha and epsilon, we want this to be asymptotically smaller than this quantity. This is the density assumption. Okay, and so basically we can study the non-backtracking random walk again. Oops. So the technique that I showed you still works, and a result says that if we take the total variation distance at 1 plus eta log Pn, this will go to 0 for every eta positive. Okay? Just to say a few words about this thing, these graphs are highly studied in number theory. In terms of the simple random walk, they have been studied by Bordenave and Laquan at first, and then by Golubev and Camper. So the simple random walk is fully understood, and here is the non-backtracking picture. This was just to say that this very simple technique not only gave us sharper answers, but it could also be generalized to other expanders, while the previous techniques of Lubetsky and Perez could not. So, okay, just to recap, today we saw the L2, how the L2 techniques can be used for upper bounding the mixing time. We talked about cutoff. Tomorrow, I will be talking to you about limit profiles, which is very closely related to cutoff. It's a sharper type of result than cutoff, actually. And again, we will be using the spectral information to study this object. I'll stop here. Thank you very much for your attention.
Thank you very much indeed, Evita. Let's unmute ourselves and thank Evita. Questions? I was actually, so I didn't quite understand the distinction between the version of the backtracking random walk that you're considering and the previous version